In my earlier video, I had discussed about integral domain with some example. Today at first I will discuss some more example elaborately. But I will recommend you, if you don't see my earlier video, please see my earlier video. Then today's video will be so easy. Today at first I will discuss one example, and this example is very important for concept of ring theory. The question is, if A is any integral domain, then the polynomial AX is also integral domain. I will prove this topic by contradiction. Consider two polynomial fx and gx, where fx equal to a0 plus a1x up to anx to the power n, and gx equal to b0 plus b1x up to bmx to the power m. Consider there exists a divisor of 0. That means consider fx times gx equal to 0, and we all of us know a polynomial will be 0 when each coefficient will be equal to 0. Since I have considered it, there exists a divisor of 0, and that means we have to consider an equal to bm not equal to 0. But notice in the question has indicated A is an integral domain. Therefore, their product equal to 0 means obviously A and Bm equal to 0. But since A is integral domain, so either An equal to 0 or Bm equal to 0, or both An equal to Bm equal to 0. Therefore, our assumption is a wrong assumption. Thus, here we have assumed A and Bm not equal to 0. But since A is integral domain, obviously one of them must be equal to 0. Therefore, when A is an integral domain, then obviously their polynomial must be integral domain. As for example, since Z is a integral domain, obviously Zx would be integral domain. Similarly, since R is a integral domain, then Rx would be integral domain. Similarly, other polynomial. Okay, now let's review the properties of ring. If R has multiplicative identity, which is called 1, we say that this is the ring with identity, and when AB equal to BA for AB belongs to ring, then R is called the commutative ring. And if R is a commutative ring with identity, and when AB equal to 0, that imply either A equal to 0 or B equal to 0, or both A and B are equal to 0, then such ring is called division ring. And when both property R is commutative ring and R is ring with identity and R has a divisor of 0, then R is called integral domain. And new concept, division of ring. Actually, division of ring means if A inverse exists, where A be any arbitrary element of this ring, means if inverse of each element exists, then this ring is called division ring. Which is more generalization of integral domain. Integral domain does not mean every element has multiplicative inverse, but division ring always imply it has a multiplicative inverse. And what is the field? Field is more restriction. A commutative division ring is a field. Now notice the diagram of ring. This is the commutative ring and this is the ring with identity. As for example, set of even integer, set of integer multiple 3 and x times zx, actually which is equal to a naught x plus a1 x, so on. Sorry, here a1 x square. Actually all polynomial whose degree greater than 1 or higher will be commutative ring without identity. And here the ring with identity, consider set of 2 cross 2 matrices with real entries. These matrices ring obviously contain ring with identity but not be a commutative ring. And commutative ring which is contain ring with identity and also contain divisor of 0, then this ring is called integral domain. And here division ring is different. Here every element has inverse, but in integral domain it does not necessarily every element has inverse. As for example integer, this is integral domain but not division ring. Division ring may or may not be commutative, but it is obviously ring with identity. And here the field, here actually more restriction at field. Field is actually both division of ring and integral domain. But here notice, here converse is not true. Integral domain does not imply always field because integral domain not be necessary division of ring. Now I will see one example, ring of Gaussian integer. We all of us know about this ring. Here 1 plus 0i be the unity. We will prove is this ring is integral domain. This ring always commutative ring. Now we have to prove is there exist any divisor of 0? Assume there exists divisor of 0. That means consider there exist two elements a plus ib and c plus id which is non-zero, and in Zi the element non-zero means either a not equal to 0 or b not equal to 0 or both. A and b both not equal to 0. Similarly c plus id, for divisor of 0 we have to prove a plus ib times c plus id equal to 0, 0. Okay? And from this it implies AC minus VD times plus I times AD plus BC equal to 0, 0. Okay? Well, of us know this is the homogeneous equation which I had to read in higher secondary. And in homogeneous equation, matrix with non-zero determinant always will be trivial solution. Since this is the homogeneous equation, so then consider the matrix A minus B, B, A with unknown vectors C and D. Consider this is the unknown vector, and we all of us know in homogeneous equation matrix with non-zero determinant always has a trivial solution. And here determinant of the matrix is A square plus B square, and which is always B greater than 0. That means there exists always trivial solution. That means this unknown vector C D would be 0, 0. Okay? And since this vector C D equal to 0 vector, so always C plus ID would be 0. Therefore, our assumption is a wrong assumption. Zi cannot be contain any divisor of 0 because here C plus ID be 0. Therefore, our proof is done. Zi is an integral domain. Now let's see. Zi is field. Consider a non-zero element 1 plus 2i, which is obviously belongs to Zi. Then the multiplicative inverse of this element would be 1 minus 2i over 1 plus 2i times 1 minus 2i, and which is equal to 1 minus 2i over 1 plus 4. This is equal to 1 minus 2i over 5, which is equal to 1 over 5 plus minus 2i over 5, and which does not be member of Zi, because 1 over 5 and 2 over 5 not be member of integer. Are you getting? That means in Zi there exists a non-zero element which has no multiplicative inverse. That means Zi is a not field. Okay? That means Zi is integral domain but not field. Now I will see one nice theorem. The theorem is every field is an integral domain. Consider A be a field and A be two elements in this field, and consider A not equal to 0. Assume A be equal to 0 in this field. We already had assumed A not equal to 0. If we also consider B not equal to 0, then obviously A and B will be divisor of 0. And since A belongs to this field, therefore every element has multiplicative inverse. Therefore, we can multiply this equation A be equal to 0 by 1 over A. Multiply both sides by 1 over A. Then by associative law, we can write it as 1 over A times B equal to 0. And we all of us know this is equal to always 1. And that implies obviously B equal to 0. Or from the equation A B equal to 0, here this implies B equal to 0. That means A and B are not divisor of 0. Therefore in this field, there exists no divisor of 0. So it must be integral domain. Okay? Therefore our proof is done. Every field always be an integral domain. Now I will see this structure Q root 2, which is equal to A plus B root 2, where AB belongs to rational number. I will say this is be a field. We all of us know this ring. This is the commutative ring with identity 1. Consider A plus B root 2 not equal to 0. Since we have to prove every element has multiplicative inverse, therefore consider x plus y root 2 times A plus B root 2 equal to 1, and that always implies x plus y root 2 equal to 1 over A plus B square root of 2. And we all of us know we can write it as A minus B square root of 2 over A plus B square root of 2 times A plus B square root of 2, which is equal to A minus B square root of 2 over A square minus 2B square. And since AB be the member of rational number, so obviously A over A square minus 2B square and B over A square minus 2B square belongs to Q. And since A and B be the member of rational number, so this is impossible. A square minus 2B square equal to 0. So always A square minus 2B square not equal to 0. Therefore, every element in this ring has a multiplicative inverse. So this ring is obviously be field. And since this is field, so This is obviously imply this is integral domain. Today I will stop here. In my next video, I will discuss this topic elaborately. But at first I will recommend you. Please go through this video with pay attention. Concept of ring theory is very important for any competitive exam. See you soon. Stay safe and stay positive. Thank you so much.